So let's say you're sitting at home with about 20 bags full of assorted electronic components. You find yourself a green LED and a couple photoresistors, and you decide that you want to make a nightlight. Well, that shouldn't be too tough, right? No problem at all. So we look at our photoresistors. We know that these change resistance depending on how much light is shining on them. So we decided we'll take a quick look at that just to get a feeling of how they behave. So we'll hook up the leads of our multimeter to the base of the photoresistor. And we can see, I can see, you can't see anything, but I'm sure you're good at reading upside down. We can see that when it's exposed to light, gives out about 10,000 ohms, maybe a little less. And when it's completely dark, 3 million ohms, 2 million ohms, 2.5. So we can use this. We'll say, we want a threshold somewhere between dark and light. So we'll say it's working sort of on voltages at 2 million ohms. That's what we'll assume, which is quite a bit. So we'll throw this in our breadboard, and we think, 2 million ohms. If I want to use some kind of voltage divider circuit or anything else to really control a transistor or a relay or a MOSFET to turn on an LED, 2 million ohms is going to be ridiculous. So that just happens to be the specification of these photoresistors. And a quick way to kind of drop that down to a more human level might be to take another one, the same type, and we'll put it in parallel. Because we know that a parallel resistive circuit is a lot less resistive than a series or a single circuit. So once again, we'll grab our multimeter, put it somewhere where you can kind of see what's going on, and we'll throw the probes around those two photoresistors, and when they're exposed to light, now we see 4,000 ohms, which is about half of what we saw before. And when I cover them both up, we've got 60,000 ohms. 60,000, that's more reasonable. I've got 30k resistors and 33k and 100k and whatever else, so that should work all right. So we need to use these in a control circuit. The only tough part is photoresistors, the resistance drops as we see more light. We want current to flow through this circuit when there's no light, so we need to use these sort of in an inverse fashion. And the way we'll do that is with a voltage divider. So we saw right there that our voltage or our resistance in the photoresistors, this little parallel circuit here, is bouncing somewhere between 5,000 and I think it was 50,000. So if we put two resistors upstream, these are both 30k resistors, totaling exactly 60,000. 60,000 ohms in series with about 30,000 ohms is our threshold. That means that 2/3 of the voltage will be burnt off up here, leaving only 1/3 for the bottom. So if we were to hook this up in our circuit, top rail, there, the current flow in here is going to be very small, obviously, because we have about 100,000 ohm circuit at this point. There's not a lot going on. If we were to hook that up, put our multimeter to the voltage setting, and I'm going to probe between ground and the junction where the resistors meet the photoresistors. And with light exposed, we're getting 0.3 volts, which is not enough to turn on a transistor. You need at least 0.6 volts to forward bias it. And as I cover them up, hopefully we'll see, just like that, the voltage increases to the point where when it's completely dark, we've got 3 volts. So we can work with that. It gets dark, voltage goes up, we can use that to trigger a light. We're almost there, the hard part's done. You just have to realize that, a voltage divider circuit is the way to go. So we've got 3 volts. We'll say that our threshold is at 2.5 volts, and we know that we want 20 milliamps. No, not even. not 20 milliamps. We've got 3 volts there. We want 20 milliamps to flow through the LED when it's hooked up. So when we throw our LED into this circuit, we'll put it upstream of the transistor. As you always should, we will put it in series with the resistor. This is a 150 ohm resistor up here, which makes sense for a 5 volt circuit. That's going to need a positive voltage signal. And just to make sure that LED is working, I'll build a quick jumper to ground. Whoa, not do that. Come back. Build a quick jumper to ground. Ground out the leg, LED comes on. So that part of the circuit's working. Now I'll take this ground and I'll put it on the emitter side of the transistor. So this transistor is looking for a base signal now. It's looking for a signal to turn on. Pretty standard a pretty standard transistor. We can assume it has a gain of about 100. So 100 times the input current will run through. If we want 20 milliamps to run through the LED, that means we want 20 divided by 100 to run through the signal circuit, which is 0.2 milliamps. 0.2 milliamps, we know that we're sitting at 2.5 volts. V equals IR, V over I. So we've got 2.5 volts divided by 0.0002. That took a second, which is a lot. That's 10,000 ohms. So we'll see what we've got in our pile of resistors here. We've got a 4.7, 33, 270, 10 million, 2.2. Let's go with a 4.7 for now. We'll see how it behaves. If our math is wrong, we'll find out pretty quickly what's going on. So this 4.7 ohm resistor, 4.7 kilo ohm resistor needs to get stuck into the base leg of this transistor. And then we will jumper from the junction of our resistors and our photoresistors to there. And this should be it. Our circuit should be hooked up at this point. There's a good look at it. No, it's kind of tough to see, but that's everything you need. And if we come in and we cover up our photoresistor, sure enough, on comes the light. So that sensitivity seems pretty good. If it was coming on too early, you could increase the resistance in that signal circuit. That 4.7 we just put in, you could up that to a 10 or up it to an 8, whatever you need, but I think that's pretty good. Try it out. We'll turn off the lights. Light comes on. Just like that. There you go. Nice and bright. So that works well.